In today's hyperconnected digital world, every app, every website, every email you send or file you download relies on a specific set of protocols, rules that govern how data moves through the internet. These protocols operate quietly behind the scenes, usually hidden beneath sleek and user-friendly graphical interfaces. But beneath that polished GUI lies a world of intricate communication and invisible transactions happening in milliseconds. And in this video, we're diving deep beneath the surface. This is not about memorizing acronyms or learning to type obscure terminal commands. This is about truly understanding what happens when you open your email client, send a file through the cloud, or simply browse your favorite website. From insecure, legacy systems like Telnet to robust modern frameworks like HTTPS and OpenPGP, we're going to dissect the digital bloodstream of our interconnected lives. Whether you're a cybersecurity student, an IT enthusiast, or someone curious about how the internet really works, this journey will change the way you think about digital communication. We'll go protocol by protocol, showing you what's happening under the hood, what your browser, mail client, or file sharing tool is really doing when you click send or connect. So grab your curiosity and let's jump straight into the protocol stack, starting with one of the oldest players in the game, Telnet. Telnet is one of the earliest application layer protocols developed for accessing remote computers. Its purpose was straightforward but powerful, to allow a user to log into another computer and interact with its terminal as if they were sitting right in front of it. Telnet functions as a virtual terminal protocol, and once connected, users could execute programs, run batch jobs, and perform administrative tasks remotely. But here's the catch: Telnet is painfully insecure by modern standards. When a user initiates a Telnet session, the server prompts for a username and password. Upon successful authentication, the user is granted access to the remote terminal. Unfortunately, none of this data, neither the credentials nor the commands sent afterward, is encrypted. Everything is transmitted in plain text, making Telnet an easy target for any attacker equipped with basic packet sniffing tools. Telnet operates over TCP port 23. When a user wishes to connect to a Telnet server, the steps are as follows. First, the system prompts the user to provide their login name or username. Next, it asks for the password. Once the system checks the credentials, a welcome message is displayed. The user is then given access to a command prompt on the remote server. And just like that, the user gains control of a system located potentially thousands of miles away. Simple. Efficient. Dangerous. Because Telnet sends everything in clear text, anyone monitoring network traffic can easily capture usernames, passwords, and session activity. This vulnerability has made Telnet obsolete in most secure environments. Today, it has been replaced almost entirely by SSH, which offers the same functionality but with robust encryption and integrity checks to protect your session. Understanding Telnet is essential because it shows us how far we've come in securing remote communication. While it's a relic in modern computing, it laid the groundwork for the secure protocols we rely on today. Next up is HTTP, or Hypertext Transfer Protocol, the backbone of the World Wide Web. Every time you open a browser and type in a web address, you are using HTTP. This protocol enables communication between a web browser, the client, and a web server, allowing you to retrieve HTML pages, images, videos, scripts, and more. It is what makes browsing the internet possible. HTTP works through a simple request-response mechanism. Your browser sends an HTTP request to a server, and the server responds with the requested content. It's like placing an order at a restaurant and having the waiter bring your meal to the table. However, HTTP, like Telnet, sends data in clear text. This means that any sensitive information transmitted via HTTP, login details, personal data, financial information, can be easily intercepted by attackers. Because of this, tools like Telnet or Netcat can be used to mimic a web browser, manually typing HTTP commands to communicate with a web server. This is possible only because the communication is unencrypted and straightforward. To utilize HTTP, two components are necessary: an HTTP client like a web browser and an HTTP server. The server hosts and serves a specific set of files in response to incoming client requests. Popular web server software includes Apache, which is open source and widely adopted, Internet Information Services or IS, developed by Microsoft and requiring a license, and Ginx, also open source and known for speed and scalability. As for browsers, the landscape is dominated by Google Chrome, Mozilla Firefox, Microsoft Edge, and Apple Safari. Despite its ubiquity, HTTP's major weakness is its lack of security. Because it transmits data in plain text, it is highly vulnerable to man-in-the-middle attacks, eavesdropping, and data manipulation. Thankfully, we have a secure alternative, HTTPS. But before diving into HTTPS, it's essential to fully understand how HTTP operates because HTTPS is built directly upon it. HTTPS is the secure sibling of HTTP. The key difference lies in the addition of an encryption layer, SSL or TLS, which stands for Secure Sockets Layer and Transport Layer Security, wrapping around the HTTP protocol to safeguard the data being transferred. Without HTTPS, secure online transactions like banking, shopping, or even logging into your favorite sites wouldn't be possible. While HTTP operates on TCP port 80, HTTPS shifts to port 443. The workflow of HTTPS mimics HTTP with one significant upgrade: all communication is encrypted. When a client initiates a connection, it begins with a client hello message containing supported TLS versions, cipher suites, and random data. The server responds with a server hello message that includes its certificate, selected cipher suite, and its own random data. The client then authenticates the server's certificate using pre-installed certificate authority or CA certificates. The client generates a pre-master secret, encrypts it with the server's public key retrieved from the certificate, and sends it. The server decrypts the pre-master secret with its private key. Both parties independently generate session keys from the pre-master and random data. They exchange finished messages encrypted with the session key, signaling that the connection is now secure. If an attacker were to capture packets during an HTTPS session, all they would see is encrypted data, because the encryption ensures confidentiality and integrity of data. This is why modern browsers warn users when a site doesn't use HTTPS. Without this security, your interactions online are exposed. That little padlock in the browser bar? It's not just decoration, it's your first line of defense in the digital world. Let's now move on to FTP, or File Transfer Protocol. FTP was designed to make transferring files between computers efficient and standardized, regardless of their operating systems. Like HTTP, FTP also sends data in clear text, including usernames, passwords, and file contents. This makes it easy to demonstrate with tools like Telnet or Netcat, and also very vulnerable. An FTP session typically involves connecting to an FTP server on port 21. Once connected, you authenticate with a username and password. There are two communication channels involved. The first is the control connection, used for sending commands and responses. The second is the data connection, used for the actual transfer of files. Popular FTP server software includes VSFTPD, ProFTPD, and UFTP. On the client side, tools like the Linux Terminal FTP client or graphical tools like FileZilla make interacting with FTP servers user-friendly. Some web browsers also support FTP natively. But again, the core issue remains: FTP is insecure. All your credentials and files can be intercepted if not protected with encryption. This is why secure alternatives like FTPS and SFTP exist. These protocols add encryption to the file transfer process, ensuring that sensitive data is not exposed during transit. But before we dive into FTPS, it's important to fully understand the risks posed by plain FTP and how widely it was adopted before secure versions became the norm. FTPS, or File Transfer Protocol Secure, is a secure enhancement of the traditional FTP protocol. While FTP transmits data, commands, and credentials in clear text, FTPS addresses this serious vulnerability by adding encryption through SSL or TLS. It retains the same overall structure as FTP, operating on the same client-server model and continuing to use both control and data channels. The primary improvement lies in how it encrypts those channels to prevent attackers from intercepting sensitive data. Understanding FTPS requires a brief review of FTP itself. FTP relies on two channels for communication. The control connection allows a client to authenticate and send commands to the server over port 21. After authentication, a separate data connection is created to transfer files and directory listings. FTP also offers two different modes for establishing data connections: active and passive mode. In active mode, the client initiates the control connection to the server on port 21, and then the server initiates the data connection back to the client on port 20. This can pose a problem when the client is behind a firewall, as firewalls often block unsolicited incoming connections from the server. Passive mode resolves this by having the client initiate both the control and data connections. When the client issues a POP3 command, the server responds with a random port number. The client then connects to this port to establish the data channel, making the entire session client initiated and firewall friendly. FTP can also operate with different data types depending on the nature of the files being transferred. The ASCII mode, also called Type A, is used for text files, converting data to and from 8-bit ASCII during transmission. The binary mode, known as Type I or image mode, transmits data byte by byte, preserving the original format of binary files. There's also EBCDIC or Type E for systems using the EBCDIC character set, and local Type LN for systems that don't support 8-bit byte transmission. Now, in FTPS, all these FTP features are preserved, but encryption is added. FTPS supports two types of encrypted connections, implicit and explicit. In an implicit connection, the entire session, including command and data channels, is automatically encrypted from the start. The client connects to port 990, and SSL/TLS encryption is enforced immediately. In an explicit connection, also called FTPS, the client connects to the standard FTP port 21 and then explicitly requests encryption using the auth TLS command. Depending on the server configuration, the control channel, the data channel, or both may be encrypted. FTPS provides essential security benefits by preventing sniffing attacks that target usernames, passwords, and file contents. By encrypting command and data exchanges, FTPS ensures confidentiality and integrity, making it a secure option for transferring sensitive information over a network. Simple Mail Transfer Protocol, or SMTP, is the backbone of how emails are sent across the internet. It is the standard protocol used to push email messages from a client to a server or from one server to another. SMTP is a push protocol, responsible only for sending emails. It does not retrieve them. For receiving email, separate protocols like POP3 and IMAP are used. SMTP typically operates on port 25 and is designed to facilitate communication between various components of the email infrastructure. These components include the Mail User Agent, MUA, which is the email client you use to compose or read messages, the Mail Submission Agent, MSA, which checks and accepts outgoing messages, the Mail Transfer Agent, MTA, which routes messages across the internet, and the Mail Delivery Agent, MDA, which stores the final version of the email on the receiving server. When you send an email, your client, or MUA, submits it to an MSA. The MSA checks the message for errors and hands it off to an MTA, which determines the destination and routes the message accordingly. The MTA on the receiving side may also act as an MDA, placing the message in the recipient's inbox. Eventually, the recipient's email client retrieves the message from the MDA. This end-to-end process can be thought of like traditional mail delivery. You write a letter and hand it to a post office clerk, the MSA. The post office processes and forwards it through a network of sorting facilities, MTAs, until it reaches the recipient's local post office, which places it in the mailbox, MDA, ready to be picked up. While SMTP is simple and effective, it transmits all information, including sender, recipient, subject line, and message body, in plain text. This makes it vulnerable to interception and spoofing. Attackers can read or alter email contents, impersonate senders, and even inject spam or phishing messages into the email stream. To counter these vulnerabilities, SMTPS, or Simple Mail Transfer Protocol Secure, was introduced. SMTPS is not a separate protocol from SMTP but rather an encrypted wrapper that protects SMTP communication using SSL or TLS. By upgrading SMTP with encryption, SMTPS provides authentication, integrity, and confidentiality. SMTPS operates over ports 465 and 587, where 465 was originally used for implicit SSL and 587 is now preferred for explicit TLS via the startles command. The startles command is critical in modern email security. When an email client connects to a mail server on port 587, it initiates a standard SMTP session. Once the server responds with its capabilities using the ELO command, the client sends the startles command to request that the session be upgraded to a secure TLS encrypted channel. Once the server agrees, both sides negotiate encryption parameters and continue the SMTP session securely. Using SMTPS ensures that email credentials and message contents are encrypted during transmission. This makes it significantly harder for attackers to intercept sensitive information, inject spam, or impersonate trusted users. Additionally, using TLS-based authentication mechanisms prevents unauthorized access to mail servers and mitigates attacks such as spoofing and phishing. SMTPS also helps enforce domain-level email policies and security practices. While it doesn't encrypt messages end-to-end, meaning mail servers can still read the email contents, it vastly improves security during transmission. In short, SMTPS transforms traditional SMTP from a vulnerable legacy protocol into a more trustworthy and secure communication channel essential for modern email systems. While SMTP is responsible for sending email, receiving email is handled by protocols such as POP3 and IMAP. Post Office Protocol version 3, or POP3, is one of the oldest and most widely used protocols for retrieving email messages from a server. It operates on port 110 and is designed for simple, one-way email delivery. The primary goal of POP3 is to download messages from the Mail Delivery Agent or MDA to the user's Mail User Agent or MUA, which is typically their email client. When a POP3 session begins, the client establishes a connection to the server, authenticates with a username and password, and retrieves new messages. By default, POP3 downloads all messages and deletes them from the server afterward. This ensures that messages are stored locally and not kept on the server, making it ideal for users who prefer offline access. However, this default behavior has some drawbacks. Synchronization between multiple devices becomes difficult, as messages read on one device won't be marked as read on others. Some clients allow users to override this behavior and retain copies of emails on the server, but it's still not a seamless experience for multi-device users. Another major limitation of POP3 is its lack of security. Like FTP and Telnet, POP3 transmits all data in clear text, including usernames, passwords, and message content. This opens the door for attackers to intercept and steal login credentials or read sensitive email contents using simple packet sniffing tools. While it may have been acceptable decades ago, such vulnerabilities are no longer tolerable in modern networks. To secure POP3, the POPs protocol was developed. POPs is essentially POP3 protected with SSL or TLS encryption, ensuring that all data transmitted between the client and server is encrypted. It typically operates on port 995. When a POP3 client connects to a server using POPs, it initiates a secure handshake using the TLS protocol. This handshake involves the client sending a hello message with its supported cipher suites, and the server responding with a digital certificate. Once the server is authenticated, both parties exchange keys and establish an encrypted session. After this handshake, the client sends login credentials, which are now safely encrypted. The user can then retrieve their messages as usual, but this time without risking exposure to man-in-the-middle attacks or network sniffing. POPs makes POP3 viable in today's security-conscious world by wrapping the otherwise vulnerable protocol in a layer of robust encryption. Although it still lacks full synchronization capabilities and is better suited for single-device use, POPs provides a significant improvement in privacy and security over its unencrypted predecessor. With Startle's support, some implementations can also upgrade a plaintext POP3 connection to a secure one on the same port, giving administrators more flexibility. In summary, POPs offers a practical and secure solution for downloading email from a server, ensuring that sensitive login information and messages remain protected during transit. Internet Message Access Protocol, or IMAP, is a more advanced and flexible email retrieval protocol compared to POP3. While POP3 was designed for simple download and delete workflows, IMAP was built for the modern world, where users often access their email from multiple devices. IMAP enables real-time synchronization between the mail server and all connected clients, meaning if you read a message on your phone, it will also appear as read on your laptop. The protocol operates on port 143 by default and maintains a continuous connection with the mail server to reflect live changes. Unlike POP3, IMAP does not automatically delete messages from the server after downloading them. Instead, it keeps emails on the server and allows users to organize messages into folders, search through emails on the server itself, and only download content on demand. This makes it ideal for accessing large volumes of email across various devices while keeping everything perfectly synchronized. However, IMAP suffers from a similar security flaw as POP3 in its default configuration. It sends login credentials and commands in clear text. Anyone monitoring the network can easily capture usernames, passwords, and even email content. For this reason, secure versions of IMAP have become essential in today's security landscape. IMAPs, or Secure IMAP, addresses this vulnerability by adding SSL or TLS encryption to the IMAP protocol. When an email client uses IMAPs, it typically connects to the mail server over port 993, establishing a secure encrypted tunnel before any authentication or data exchange occurs. This ensures that all communication between the client and the server, including the login process, folder structure, and message content, is protected from eavesdropping and tampering. IMAPs follows the same encryption mechanisms as other TLS-enabled protocols. When a client initiates a connection, it sends a hello message specifying the TLS version and supported cipher suites. The server responds with its certificate and agreed encryption parameters. Once the client authenticates the server's identity, the two exchange keys and generate a shared session key used to encrypt the session. This session key ensures confidentiality, integrity, and authenticity for the entire IMAP communication. IMAPs is widely supported by all modern email clients and is considered the best choice for anyone looking to maintain access to a synchronized inbox while also ensuring the security of their communications. Whether you're using a smartphone, tablet, or desktop, IMAPs makes sure your inbox is consistent, accessible, and encrypted. To better understand how protocols like HTTPS, FTPS, SMTPS, POPs, and IMAPs achieve encryption, we need to explore the foundation of secure internet communication, the SSL/TLS protocol. SSL, which stands for Secure Sockets Layer, and TLS, or Transport Layer Security, are cryptographic protocols designed to secure communication between a client and a server. SSL is now considered outdated, and TLS is the standard used today, with the latest versions offering significant security improvements. Think of TLS as a protective wrapper that encrypts other application layer protocols. For example, wrapping HTTP with TLS creates HTTPS, wrapping FTP gives you FTPS. The process that makes this possible is called the TLS handshake. It's a multi-step exchange that takes place before any encrypted data is transmitted. It begins with the client sending a client hello message to the server. This message contains the TLS version, a list of supported cipher suites, and a randomly generated value called the client random. In response, the server replies with a server hello, which includes the server's chosen cipher suite, its own random value, and its digital certificate. This certificate, issued by a trusted certificate authority, proves the server's identity and contains its public key. The client then validates the certificate using its pre-installed list of trusted authorities. If everything checks out, the client generates a pre-master secret and encrypts it with the server's public key, sending it back to the server. The server decrypts the pre-master secret using its private key. Now, both the client and server possess the client random, the server random, and the pre-master secret. Using these three values, both sides derive the same session key independently, without ever transmitting it. Finally, both sides send a finished message encrypted with the session key, indicating that the handshake is complete. From this point onward, all communication between the client and server is encrypted using symmetric encryption, ensuring high performance and robust security. The beauty of the TLS handshake lies in its combination of asymmetric and symmetric encryption. Asymmetric encryption is used initially to securely exchange information and authenticate the server, while symmetric encryption is used for the actual data transfer because it's faster and more efficient. TLS not only ensures confidentiality, so no one can read your data, but also guarantees integrity, so data cannot be modified in transit, and authenticity, so you know you're communicating with the real server. TLS also assigns standard ports for each encrypted protocol. For example, HTTPS uses port 443, FTPS uses port 990, SMTPS uses 465 or 587, POPs uses 995, and IMAPs uses 993. These ports signal to both client and server that encrypted communication is expected from the start. Without TLS, the modern internet as we know it would be impossible. Online banking, private messaging, and secure file sharing all rely on TLS to function safely. And with the increasing sophistication of cyber threats, adopting TLS-based secure versions of traditional protocols is no longer optional, it's essential. Another critical aspect of modern internet infrastructure is DNS, the domain name system. It acts as the internet's phone book, translating human-readable domain names like example.com into IP addresses that machines understand. When you visit a website, your computer sends a DNS query to a DNS server, asking it to resolve the domain name into an IP address. The server replies with the appropriate record, and your browser connects to the destination. While incredibly convenient, this process has a major flaw: it's unauthenticated. Any attacker on the network can forge a fake DNS response and redirect users to malicious websites. To solve this, DNSSEC, or DNS security extensions, was introduced. DNSSEC adds a layer of verification to the DNS process, allowing clients to confirm that the DNS response they receive truly comes from the domain owner and has not been tampered with. It does this by using digital signatures. The owner of a DNS zone signs all DNS records using a private key and publishes the corresponding public key in the DNS zone as well. When a client receives a DNS response, it also receives the associated digital signature. The client then uses the published public key to verify the signature, confirming that the data is authentic and hasn't been altered. By implementing DNSSEC, DNS gains two critical security properties: authenticity and integrity. Authenticity ensures that the DNS response is truly from the domain owner, while integrity guarantees that the response hasn't been modified in transit. DNSSEC doesn't encrypt the DNS query or response, it simply makes it verifiable. This makes it especially useful in preventing attacks like DNS spoofing and cache poisoning, which can redirect users to malicious sites even when they type the correct domain name. With DNSSEC, such attacks become significantly harder to execute. Although adoption has been gradual, major registrars and DNS providers now support DNSSEC, and it is becoming an increasingly important component in securing the Internet's foundational infrastructure. With traditional email protocols like SMTP, POP3, and IMAP transmitting messages in plaintext, even after the introduction of SSL/TLS encryption layers, some users demand even greater levels of privacy. This is where OpenPGP, or Pretty Good Privacy, comes into play. OpenPGP is an open standard for encrypting and signing data, including email messages, ensuring that only the intended recipient can read the message and verify its authenticity. While TLS secures the transmission path between email clients and servers, OpenPGP secures the content itself. This means that even if the email passes through multiple intermediate mail servers, no one, including the servers, can read the message content. OpenPGP uses asymmetric encryption, where each user generates a pair of cryptographic keys, a private key and a public key. When sending a message, the sender uses the recipient's public key to encrypt the content. Only the recipient can decrypt it using their private key. Additionally, the sender can sign the message using their own private key, and the recipient can verify the signature using the sender's public key, confirming the message's authenticity and integrity. To use OpenPGP, users typically install tools like GNU-PG, the GNU Privacy Guard, which is a free and open source implementation of the OpenPGP standard. Once installed, users can generate their key pairs with a simple command line instruction and integrate GNU-PG into their email clients for seamless encryption and decryption of messages. Even if the email is intercepted, the content remains a scrambled mess to anyone lacking the appropriate private key. This level of encryption is ideal for users who want to maintain complete confidentiality over their communications, especially in environments where privacy is a matter of personal safety. However, it's worth noting that OpenPGP protects the message body but not the headers, meaning metadata like the subject line or sender address is still exposed. Nonetheless, OpenPGP remains one of the most powerful tools for achieving true end-to-end encryption in personal and professional email communication. Another game-changing protocol in secure communication is SSH, or Secure Shell. Designed to replace insecure protocols like Telnet and Login, SSH allows users to remotely connect to and administer computers over an encrypted channel. It's especially popular in system administration, penetration testing, and secure file transfer. When you use SSH to connect to a remote system, everything, from your login credentials to the commands you type, is encrypted. This prevents attackers from intercepting passwords or modifying command traffic mid-transit. SSH uses port 22 by default and supports two main authentication methods, username and password, or public-private key pairs. In key-based authentication, the server stores the user's public key and verifies that the client holds the corresponding private key during the login process. This method is far more secure than passwords, especially when paired with passphrases and restricted key permissions. The first time a client connects to a server using SSH, it is asked to verify the server's public key fingerprint. This helps prevent man-in-the-middle attacks. Once authenticated, the user gains access to the server's terminal as if they were sitting in front of it. SSH can also be used for secure file transfers via protocols like SCP, Secure Copy Protocol, or SFTP, SSH File Transfer Protocol. Whether you're deploying code to a web server, managing cloud infrastructure, or transferring sensitive data, SSH is the tool of choice. Its reliability, speed, and built-in encryption have made it a standard in secure remote communication. In scenarios where direct communication between two systems is blocked by firewalls or filters, SOCKS5 offers a smart workaround. SOCKS5 is a proxy protocol that acts as a middleman between a client and a server, allowing data to be relayed through a third-party system. For example, if user A wants to access client B, but a firewall prevents direct access, user A can connect to a SOCKS5 proxy server. The proxy server then forwards the request to client B, making it appear as though the connection originated from the proxy. This technique is commonly used for bypassing regional restrictions, hiding IP addresses, and securing traffic from surveillance. SOCKS5 improves on earlier versions by supporting authentication, UDP traffic, and enhanced security features. The handshake process begins when the client sends a version identifier and authentication methods. The proxy replies with its selected method, and once authenticated, data transfer begins. Since SOCKS5 operates at a lower level, it can be used with many protocols like HTTP, FTP, and SMTP, making it incredibly versatile for anonymizing traffic or accessing blocked services. Lastly, the Server Message Block Protocol, or SMB, plays a critical role in file sharing, especially within Windows environments. SMB allows users to share files, printers, and other resources across a network. With SMB, users can access remote files as though they were stored locally, enabling seamless collaboration across workstations. SMB also supports authentication, access control, and user sessions, allowing network administrators to enforce permissions and secure access to shared resources. Modern versions of SMB, especially SMB3, X, include features like encryption, performance improvements, and fault tolerance. SMB typically uses port 445, and older versions may also use port 139. Because SMB is often targeted by malware and ransomware, such as the infamous WannaCry attack, it's crucial to restrict SMB traffic to trusted networks and keep systems updated. Protocols like NTLM and Kerberos are often used in conjunction with SMB for authentication. On Unix and Linux systems, SMB support is typically provided by Samba, a software suite that enables interoperability with Windows networks. Whether you're accessing shared folders in an office, mapping network drives, or managing printers, SMB is quietly doing the heavy lifting behind the scenes. And that brings us to the end of our deep dive into widely used network protocols, both the classic workhorses and their secure modern counterparts. These protocols power the invisible machinery of our digital lives. They shape how we browse, communicate, share files, and stay connected. Understanding them doesn't just make you a better IT professional, it helps you appreciate the intricate, high-speed choreography of data that takes place every time you go online. So the next time you click a link, send an email, or connect to a remote server, you'll know exactly what's happening under the hood. Thanks for watching. Always stay curious, keep learning, and stay